Welcome. Today we're going to talk about continuity and other things. Friends, well, acquaintances, things that are related to continuity. For example, one-sided limits, theorems related to it, and piecewise defined functions. I think they're friends. We'll see. One-sided limits, what are they? Well, look at this function. What is the limit as we approach A? What value do they come to? They don't. Not that value, because they're approaching here from the top, but they're approaching here from the bottom. Those are different. What value are they approaching? There is none. So the answer is does not exist. There is no limit. But that's not the whole story, because clearly there are two very well-defined limit points coming from one side or the other. So what we have is the one-sided limits do exist. The one-sided limits do exist. How would you write a one-sided limit? You could write like a 1 on one side, but that doesn't make any sense. What we really have here is numbers that are bigger than and numbers that are smaller than. So all we need is something that can tell us about biggers and smallers. And we have actually something already in the math language to describe that. There's greater than and less than, but those aren't the ones I'm talking about. We have plus and minus. If we attach them to our limit in some way, we can tell which side we're coming from. So what we have is the left limit. The limit as x approaches a from numbers that are smaller. This is the left limit. There's also the right limit. Numbers that approach a from the right. If you want a one-sided limit, what you do is you attach a minus sign or a plus sign after the number. So this is the left limit. The left limit is clearly defined as minus 2 here. The right limit is clearly positive 3. Now notice, for the limit to exist, these would have to be the same. If both of these are the same, they are the limit. But if they're different, they still exist as themselves. Now, how is this related to continuity? Well, continuity is one step further than limits. A function is continuous at a point, x equals a, when the limit exists, not just the left or the right, but both sides going to the same place. The function's value exists at that place, and they're the same. Now, do you really only need all of this? This last one sort of implies these two, but it doesn't say it officially. So really, you have to have the limit, the point has to be there, and it has to be in the right spot that you want it to. What are some examples of continuous functions? Well, polynomials are continuous. They're continuous everywhere. Rational functions are continuous almost everywhere. They're continuous everywhere they're defined. So at the bottom of 0, they're not. Everywhere else, yes. Sine and cosine are defined. Everywhere they're continuous. Exponential functions are continuous. Logarithmic functions on their domains are continuous. In fact, almost everything you know as a function is continuous. You have to do something weird to get a discontinuity of any usefulness. Some examples of discontinuous functions are the floor function. So for example, the floor of 3.97 is 3. The floor of 4.02 is 4. So you can see there's going to be a jump. What kinds of discontinuities are there? A discontinuity is when it fails to be continuous. There are jumps like this. Another kind would be the holes. We've looked at some of those before with limits, where the limit exists, but there's nothing there. Jumps, holes. There's a third kind of discontinuity. It's called a vertical, where the function suddenly fails at a point. But we don't have to worry about that right now. What I want to do is talk about the rule. This is the powerful rule that allows us to evaluate almost all limits without any kind of issues. Now, if a function is continuous, in other words, if it deals with all these things, doesn't have a 0 on the bottom, and it works nicely, then the limit is simply plugging the value in. Now why is that? Because that's what continuity means. Continuity means you can plug the value in to get the limit. So I said we can't really find easy examples of discontinuous functions. So we have to create things. These are called piecewise defined functions, where we define them in pieces. This says, for x less than 5, it's 3x plus 10. At x equals 5, it's 25. It's 12. And above there, it's quadratic, like that. This is a discontinuous function because it's got different pieces that don't agree. So let's take a look. As x goes to 5 plus, that means we're talking about the stuff bigger than it, right there. What is the limit? Well, what's the limit of this? This thing, this piece right here is continuous. So what's its limit? It's going to be 5 squared minus 15 equals 10. Now, what about the next one? I'll pause for 2 seconds while you think it out. What's the limit as x goes to 5 from the minus side, from the less than side? Okay, so what it is, we're going to take the stuff that's less than, right here. As x goes to 5, we have 3 times 5 plus 10 is 25. Now what about the limit as x goes to 5 in general? I'll give you another 2 seconds. Okay, if you said 12 here, because that's the other one, that's not the right answer. The right answer here is does not exist. Why? Because these are different. It's coming in, actually it doesn't even look like that, it comes in higher like this. I drew it wrong to be confusing. Now, here's the thing. This and this are different. It's doing that. It doesn't have a limit. This doesn't equal that. The limit's what happens nearby, not what happens here. One more case. This one's going to be continuous. It doesn't say that. Suppose g of x is continuous. Well, that's what g of x is. Find a. That's this thing. What do we know? If it's continuous, step over here. The limit exists. From both sides, it's the same. The value exists, and it's equal. The limit exists from both sides. Well, what is the limit as x goes to 2 from the minus side? Well, we're going to take 2 from the minus side. That's this one. We're approaching 2. X becomes 2. We get 2 plus 2a. Because we don't know what a is, but it's there. What about the limit from the positive side? We get, plug it in. We're talking about this one. Now the equals doesn't matter for this. It's fine, it's good for us. But that means 2 squared plus 3 is 7. Now what do we know? The limit, not the left, not the right, but the limit exists. So that means these are the same. So 2 plus 2a is 7. Do a little algebra. You get a is 5 halves. And there you go. Continuity is a very, very powerful concept. We've only scratched the surface, and we'll do more later, but this is a start. Until next time.